Hi, I'm Michaela, and in this video I'll be showing you how we can perform Retrieval Augmented Generation using KDB.AI and LangChain. Before we dive in, I just want to mention if you want to follow along with this video, you'll need to do two things. The first one is signing up for a free KDB.AI cloud account, so you can do that over on our website KDB.AI. You'll see a big button in the top right hand corner saying sign up, so you can head there. And once you're signed up, you'll have your own free KDB.AI database where you can connect on. And if you'd like some more details on that sign up process, or you want to find out more about what this screen is showing once you're logged in, this is what it will look like, you can check out the video linked below. The second thing you're going to need is a link to this example and the dataset I'm using here today. So this is available on our GitHub, and you can get there by clicking the link on our Learning Hub, which you'll find at the top of the KDB.AI page. There is a few different samples if you scroll down the page, and we're using the LangChain and RAG one today. That's it, that's all you need. You can download this on GitHub and we can get started. So let's start by understanding what is Retrieval Augmented Generation. So large language models like ChatGPT are really great, but they are trained on static data. So, for example, if you ask ChatGPT a question today about something that happened in the past week or the past year, you won't get an accurate answer returned. And this is what Retrieval Augmented Generation, or RAG, as I'll just refer to it for the rest of the video, aims to solve. And what it allows you to do, as you can see in this diagram, is combine an LLM also with your own relevant contextual data. So when you're passing in your query, it's able to join in enhanced knowledge databases, things like your own proprietary documents if you're in an enterprise, for example, and private information can be added in here at this point and then sent to the LLM, meaning the answers generated provide more contextual and up-to-date data in their answer rather than just relying on the LLM on its own. So we're going to show how to do this on a text document today using LangChain, OpenAI, KDBAI, and various LLMs. So let's get stuck into the example. A quick overview of what we're going to cover in the sample. We're going to start by loading and chunking our data, which is a text document. We're going to create some vector embeddings and store this in KDBAI. And then we're going to perform RAG on this data set to get some contextual answers back. So very first thing we need to do is set up. So we're going to just load in the relevant libraries. We've got our libraries needed to talk to KDB.AI. We've got our LangChain libraries here. And then we need to set some API keys. So I've gone ahead and done this off camera, but you will need to go to both OpenAI and Hugging Face if you want to follow along. The links are provided here. You can create both keys for free. And once you have the credentials, you can just add them in here. Okay, so that's the setup complete. And we can get started loading our document and chunking it ahead of creating our embeddings. The example we're using is a text file that contains a State of the Union message from the President of the United States to the United States Congress. So we're going to split our document into chunks. First of all, we're using text loader to load it in. And then we're going to use this recursive character text splitter, which is a chunking method that comes with LangChain. Now, there's many different ways to chunk text, and the one you choose will depend on a range of factors. So when you're considering what kind of chunking method should I use, you should ask yourself, what embedding model will you be using later on? So for us, we're going to use this ADA002 model, which works well with this recursive character text splitter. If we were using something like sentence transformers, we might decide to then instead split our data by our sentences rather than by a fixed length. So with recursive character text splitter, it's been split into chunks of 500 here. There's a few other things you might consider, like your queries that you'll be using at the end, how you're going to use those queries in your application, what's the nature of the content and the size of your data, and so on. So we're going to use recursive chunking. As I mentioned, it's a good match for the OpenAI ADA002 embedding model. And it is good to note here when we're selecting our chunk size, we also need to consider our LLM token limit that we will have later on. So for example, we'll set a token limit later on above 500. So that is something to consider. If your LLM you want to use has a limit, your chunk size would need to be smaller than that. Okay, so we can see the first chunk here once we've run these few lines. This is the beginning of the document, so it's just addressing the speaker and the vice president and so on. And then as we go through the indexes, we'll see we're getting into the actual State of the Union message itself. Okay, great. So as I said, we've chosen to use this OpenAI ADA 002 model. There's various models we could have used. Actually on the OpenAI website, if you go to this link here, they do actually say that the ADA 002 one is recommended for most use cases. And they also say that it's usually going to be faster and cheaper for you. So that's worth bearing in mind. The other thing we can note on the OpenAI documentation page is our output dimensions here. So for the model we've chosen, we can see the output dimensions is 1536. So this is important when we're defining our index in the next step. So you will need to know your output dimensions if you're choosing a different model. As well, this is how you'd find out your max input tokens, as I mentioned before. That relates to the size of the chunk you will choose. Obviously, we've chosen 500, which is well below the max input tokens, so we're safe. Okay, now to set up KDB.AI for storing this data, we need to first connect. So I'm going to use my URL endpoint and API key. They're available in your cloud portal that you signed up for at the beginning of this video. And once you've defined those variables, we can connect using this session command here, passing it our key and endpoint. Okay, now we're connected to KDB.AI. The next step is to define a schema for our KDB.AI table, where we're going to store our embeddings. So we can add additional columns here, like in this case, we're adding ID and text. We also need to define our vector index here. So this is where we would specify the dimensions. So remember, we've seen that over on the OpenAI page here, the output dimensions. And then we're also specifying our similarity metric. So we're using L2 or Euclidean distance here. And in the type field here, we define our index, and we're choosing to use flat here. So we can play around with different types of metric and type or index. And if you want to know more information about those, you can head to KDB.AI. We've got a few different articles going through the different indexes and similarity metrics that you can use. Okay, so let's run our schema. That's been defined. We have a cell here just before we actually create our table. It's just checking if it exists already. If it does, it's going to delete it. If not, nothing will happen. So now we've created our table, we're able to finally use LangChain to store our data. So everything up to the point here has been data preparation, setting out the models we want to use, and then also our KDB.AI setup. So when we're going to save our data using LangChain, we use the from text command here rather than using insert, which we'd use with just plain KDB.AI on its own. And you see we have to specify a few parameters here. So including table name, our text data here, which is our chunk of data, all our chunks of data, and then our embeddings model that we've chosen to use. Okay. So once this is run, our data is stored in KDB.AI and is available to query with LangChain. Before we jump into doing RAG, let's just do a quick similarity search to see how that works. So it works as you would expect. We pass it in a query. We then run this similarity search command. Just passing in the raw query. The embedding will be done for us on the LangChain side. We don't have to do that ourselves. And then we can see the query result here is returning the most similar result. This is an okay start. Obviously, if we wanted more than one result, it might be hard to read and summarize them. And that is where RAG is going to come in. It's going to bring in the question answering to return a better summary of the response that's more human readable too. Okay, so let's jump into our Retrieval Augmented Generation piece. Now, there are a few different ways to perform this using LangChain. The most basic of these being this load QA chain up the top. And it performs QA over all documents passed. So it's quite a simple method, but it can become quite slow with larger data sets. The rest of the methods listed here build on top of this one in some way, but we're just going to look at the first one and then the second one, Retrieval QA, for today. This Retrieval QA one first retrieves the most relevant chunk of text and then does QA on that subset. So it can be a lot more efficient, but there is a risk of losing some context from the documents, obviously. Let's start with the more basic of the two, so this load QA chain. And we're going to set up two questioning and answering chains for different models, one from OpenAI and one from Hugging Face, just to see is there a difference and can we use both in the same way. Remember, we defined our API keys for these earlier in the notebook, so you'll need to have them set to be able to run the following cells. And note as well, it's this point we set our tokens for the LLMs. So remember I mentioned earlier we can tell the max input tokens, so we're going to just make it a little bit bigger than our chunk size, so 512 for both here. We're choosing this DaVinci model from OpenAI and this Flan model from Hugging Face. Okay, I think we can ignore this version warning. That is not going to affect our output here. Then in the next cell, we're passing it to load QA chain with this chain type of stuff. And that chain type of stuff parameter just means it's taking a list of documents and inserting them all into a prompt, which is getting passed to the LLM. So it's the most basic version of this chain type parameter. Again, OpenAI has good resources and documentation on these different types and parameters, so you can check out there to read more. So we're setting up one for both our LLMs, and we've got the same query as before that was returned from our Similarity Search. And we're going to pass that as our input documents here, along with the actual question itself. And you can see our question that we've asked, which was, just jumping back up here, what are the nation's strengths, has now been answered. The America's people's strengths. That's an okay answer, I guess. We can try the Hugging Face one and see what it says. So we are the only nation on earth that has always turned every crisis we faced into an opportunity. So they're pretty good. I think in previous times we've ran this, sometimes the OpenAI one is longer, sometimes the Hugging Face one is longer. So it seems to vary quite a bit depending on when you run it, what you get back. In fact, I've just ran that a few times now, and you see we get sometimes a longer sentence back from the OpenAI one. This one looks like a better result. So the nation's strengths are the American people, their ability to turn crisis into opportunities, and their capacity to turn possibilities into reality. So potentially that could be a better result the third or fourth time we've ran it there. Okay, let's take a look at our second method, which is Retrieval QA with GPT 3.5. We're just using a different LLM here for a change. And we have a few more parameters needed for this method. Most important of these is retriever, which uses this as retriever method here, which is just converting our vector database into a retriever, which can then return documents given an unstructured queries passed to it. So running this and passing our query in, printing it out, we should get a slightly different result here and a summary from the LLM. So you can see with this retriever method, we're perhaps getting a lot more detail and information, which is interesting to note. And if we try a different query, so asking it about what are the things this country needs to protect, we see we get quite a detailed answer here. We get actually, this is all nested at the minute, but this is all separate bullet points here. So we have 1 to 9 bullet points reasons, or 1 to 10 actually, of what the things are this country needs to protect. So it obviously found quite a lot of information in the document that we've passed it on this question. So this really demonstrates how you can enhance the input with your contextually specific data. So in this case, the State of the Nation document. And that's what RAG really allows you to do. It empowers these large language models to produce responses that are a lot more precise, and they're better suited to obviously the question and the context that you're asking it. You can imagine this is really useful in enterprise scenarios where, you know, really extensive fine tuning may not be feasible. So RAG is a more efficient and economically viable approach, delivering personalized and also more informed, especially with, say, private or proprietary data. That's the kind of results you can get back. Okay, that's it for this video. Don't forget to subscribe to the channel to keep up to date with all the latest from KX. Thank you.